Alright, let's talk about volatility. Although they both start with the same letter and they kind of sound similar, be careful not to confuse volatility with viscosity. They are very different properties as they both relate to intermolecular forces, but volatility kind of looks at the opposite trend. And specifically, volatility is the tendency of a liquid to evaporate. We sort of dealt with this a little bit when we talked about Dalton's law of partial pressures and how the vapor pressure of a liquid has to be considered in terms of the total number of gas particles present at some given total pressure. But technically speaking, the tendency to evaporate is the opposite of the tendency to break intermolecular interactions among molecules. They are related to each other, but it's an inverse relationship. So if you think of it this way, here you have a liquid in your beaker, and some amount of it will want to evaporate. And since the evaporation leads to gas particles that are farther apart from each other, um, you're basically looking at how much energy needs to be put in just to make that happen. And since we're looking at the tendency of the gas particle to be present, we're actually looking at the after effect, the aftermath of breaking apart intermolecular forces. You're going to have more gas present as a vapor if the intermolecular forces present in the liquid are weak to begin with. However, if the intermolecular forces in the liquid are strong, you're going to have less and less and less vapor pressure present. So, long story short, as the intermolecular forces of attraction increase, the volatility decreases. And this is why I'm telling you, don't confuse viscosity with volatility, because viscosity goes up as intermolecular forces go up, but volatility does exactly the opposite. So for your molecules here, right, you have long dispersion forces for your hydrocarbon on the left, dipole forces for your hydrocarbon containing carbon-oxygen bonds, and you have your hydrogen bonding for your hydrocarbon and water, right? And so the volatility of this species do decrease when you go from left to right. In fact, the molecule here is basically a gas at room temperature. This molecule here on the right side is easily turned into gas just by providing a little bit of energy. Even room temperature will probably generate this as a gas. Methanol CH3OH requires some amount of heat to turn into a gas, but it will have some vapor pressure. And water itself, even though it's kind of low, there is some vapor pressure for water, right? We call it humidity, really. But we're going to go a little bit more, and this is the one section in the entire lecture that will be a little bit more mathematically inclined, because we're going to try to approximate and correlate the vapor pressure of a liquid in regards to its temperature. And there's actually a relationship, one in which not the regular vapor pressure, but rather the natural log, so ln of the vapor pressure, plotted against the inverse temperature of the liquid, gives a straight line of negative slope. And that negative slope itself is correlated to the negative enthalpy of vaporization of the liquid divided by the R constant in units of joules per mole Kelvin. This is known as the Clausius-Clayperon equation. And we're basically going to use that to determine the vapor pressures at different temperatures, or determine the enthalpy of vaporization of a liquid based on the vapor pressure of the liquid and the temperature at which it's being held. Alright, now, like any good old linear plot, we have a linear equation, y equals mx plus b. The y in this plot is the ln of the vapor pressure, the x is the 1 over t, and the slope of this line is the negative delta H vap over R. So what we have here in terms of y equals mx plus b is the following equation, which if we select a data point, and if we move the slope times x, so mx, to the left side of the equation, we're going to have ln of p plus delta H vap over RT, and that will equal the y-intercept. So if we select a data point, P1 and T1, we basically have all of that equaling the y-intercept. But you could easily select a second data point, P2 and T2, where the ln of P plus delta H over RT will still equal the y-intercept. Therefore, ln of P plus delta H over RT for the first set will equal the same format for the second set. And if you basically rearrange this, in other words, bring the ln of P1 to the right side and move the delta H VAP over RT2 to the left side, you're going to end up with the following format for the equation. Now, anytime that you subtract logs, you could combine the things inside the logs as a division. So ln of P2 minus ln of P1 is the same thing as saying ln of P2 over P1. And here on the left side, we have delta H VAP over R, which is basically constants. So you can factor that out to ultimately lead to negative delta H VAP over R multiplied by 1 over T2 minus 1 over T1. And over here we have ln of P2 over P1, which is what we call, and here now rearranged in the proper form, is what we call the Clausius-Clayperon equation. Technically, it's the 2-point formula of the Clausius-Clayperon equation, but this is the one that we get to use most usually. But just be aware that if you were to actually have data points for various vapor pressures at various temperatures, you could actually plot ln of P versus 1 over T. The T will have to be in Kelvin, of course, to yield this straight line that has a slope of negative delta H VAP over R. And from the slope, if you just multiply by the value of R, you get the delta H VAP value for the given liquid. So let's do an example of this, right? Just a few things though before we do that. Delta H VAP is given in kilojoules per mole. The R constant, however, is in joules per mole, so when you use the slope to calculate delta H VAP, don't forget to change the joules to kilojoules. The temperature has to be in Kelvin, and the pressure actually could be in any units. It doesn't really matter as long as both P2 and P1 have the same units. That one doesn't really matter because you have a ratio of them, so the units cancel out regardless, but they have to be the same unit. Okay, so let's do an example. Diethyl ether. We know this has a vapor pressure of 100 torr. Oh, and by the way, since we're talking about pressure, you definitely need to refresh on your conversion factors for pressure. Atmospheres, torrs, millimeters mercury, and even pascals, just to be on the safe side. All right, so we have vapor pressures of 100 torr and 400 torr at negative 11.5 and 17.9 degrees Celsius. We're going to use that information to calculate the enthalpy of vaporization, which means that since we're mentioning enthalpy of vaporization and we have vapor pressures, those two things alone should tell you this is the Clausius-Clayperon equation you're dealing with. Alright, so we're going to plug in the values. Now, one thing you have to be careful about is to associate P2 with T2. So 100 torr goes with a negative 11.5 degrees Celsius. 400 torr goes with a 17.9 degrees Celsius. And you have to make sure to change the negative 11.5 and the 17.9 to Kelvin, so you add 273 to each of them. And so your T2, which is 17.9 plus 273 is 290.9, and the negative 11.5 plus 273 is your 261.5 Kelvin, your T1. Alright, and you do the same thing here, P2 over P1. So just make sure to keep those straight, and it might even be better for you to write on the left side, P1 equals 100, P2 equals 400. T1 equals negative 11.5, which then you convert to Kelvin, and T2 equals 17.9, which you also convert to Kelvin. And so you end up with the following expression here. If you carry the subtraction of the fractions on the right side of the equation, you should end up with negative 3.865 times 10 to negative 4 per Kelvin, which will cancel out the Kelvin units, and you'll end up with ultimately delta H VAP multiplied by numbers. So if you divide negative 3.865 times 10 to negative 4 by 8.3145, you're going to end up with a new number. Or alternatively, you could solve for delta H VAP at this point, multiply by negative 8.3145 and divide by negative 3.865 times 10 to negative 4. Your kelvins will cancel out and end up with joules per mole. The last thing to do, of course, is to convert the joules to kilojoules by using the proper conversion factor. And that will basically give you the units of kilojoules per mole for you delta H VAP, which in the case of diethyl ether is 29.82 kilojoules per mole. Alright, so this is an example of how to use the Clausius-Clayperon equation. In this case, the enthalpy vaporization was the unknown, but in any problem involving this equation, I could make P2, P1, delta H VAP, T2, or T1 the unknown. Those are all the variables that I can use. And I have to give you the values for the other four for you to find the fifth one. But just keep in mind that in future problems, you may be solving for the partial pressure of one of the components, or you may be solving for the temperature, as opposed to delta H VAP. And in that case, you gotta remember to plug in the value of delta H VAP not in kilojoules per mole, but rather in joules per mole. Otherwise, the ratio that you have here, delta H over R, will not cancel out. All right, I'll stop this right here, and I'll continue in the next video.